Good afternoon, everyone. Welcome to YSI's webinar. Thanks for joining us today. I'm Shannon Miller, and I'll be moderating. And joining me today are instrumentation experts Justin King, who's our process instrumentation product manager, and John Welsh, senior product manager for Xylem. Today, they'll be reviewing best practices for wet chemistry analyzers, maintenance on wet chemistry analyzers, and performing live hands-on demonstrations of maintenance procedures. This is part 3 of our webinar series, How to Get Optimal Data with Online Instrumentation. And parts 1 and 2, Best Practices for Online Sensor Maintenance, are available at ysi.com. Just a couple of quick things before we get started. This webinar is eligible for CEUs through the IACET and will provide more information on how to get those in a post-webinar email. We will be taking questions throughout the webinar and answering them at the end, so feel free to use the Q&A and chat boxes in Zoom throughout. We'll answer as many of those as we can. And lastly, this webinar is being recorded, and the recording will be available to watch on demand in a few days. There will also be a link to that in the post-webinar email. And with that, I'm going to go ahead and turn it over to Justin to get started.
All right. Well, hopefully you can hear me. As Shannon said, I am the product manager for process instrumentation here at Xylem, and I'll be kicking off this webinar. I'll be doing the first half, and John Welsh will come in for the second half. During this first half, we're going to talk about online wet chemistry analyzers, specifically for orthophosphate and NH4 measurements, which is ammonium. Today, we have the ELISA IQ PO4, the orthophosphate version, as a demonstration unit. The ELISA IQ is a part of our IQ SensorNet platform, which is online process instrumentation that goes into drinking water and wastewater plants and provides data back to operators to, create a more efficient process and control and monitor for regulatory compliance. You might know, if you're familiar with our product line, the 2023G, you'll see that throughout the demonstrations of this webinar today, which is our controller. The 2023G can control up to 20 parameters of the IQ SensorNet system, and it is a very nice controller. You'll see it throughout the demonstration. So without further ado, let's get into this webinar. I'd like to start by just going over the basic components of an online wet chemistry analyzer, just so we can build a basic foundation for what we'll be talking about when it comes to maintenance activities for this analyzer. So I'm going to walk you through what's basically the analyzer anatomy, is what I like to call it. And we'll start from the filter and go all the way through the analyzer and end at the drain. And these components that I'll be stopping and pointing out are pretty common for any colorimetric analyzer that you're going to see in the field. And you'll see some similarities between the ELISA here and the 3017M when John goes, but there are a lot of differences, not just the size in the instruments. So let's go ahead and get into it and start with the filter. So this is the filter that goes with the ELISA IQ. A lot of manufacturers will have some sort of filtration at the beginning to filter out the sample. We don't want particulate matter getting anywhere close or into any sort of wet chemistry analyzer. In a lot of cases, we're using microfluidics and small tubing sizes, and we want a very clean sample, so we pull in the sample that needs to be measured, and we leave all the particulate matter in that out of the process. And that starts with a filter. So this is an in situ filter. So there's a connection point up here where a tube will connect this to the sample pump, which we'll get into in a few minutes. And you drop this down into the process, and sample is being filtered through this filter medium and coming up through the tube and into the analyzer. This one in particular is a 0.45 micron filter, and it lasts at least a year. And in a lot of cases, we see these last 2 to 3 years. And this filter medium, this white part, is the consumable part. So that'll need to be changed. And it's all dependent on the process, really. So, as a general note, as we go out throughout this webinar, and as you think about process instrumentation as a whole, the closer you deploy something to the influent, the dirtier their water is going to be. That means you're going to have to touch it more frequently. If something's deployed on the effluent, the longer it'll last, because ideally the water is getting cleaner throughout the process, right? So that just depending on where you deploy these things is going to be a big factor in how much you're going to have to touch them as far as maintenance goes. And that's the same thing with that filter I was just showing. And it'll be the same thing for a lot of the components in here. So without further ado, I'm going to open up the ELISA. First, I'm just going to quickly prepare it to open because there is some temperature balancing that needs to happen. And all right, it's ready to be opened. So I'm going to go ahead and open it here. And we will start on this side. So we've got the filter, it's filtering. The sample pump is right here. And the sample pump is a diaphragm pump. It is, it can measure from, or it can pull a sample from 65 feet away. It's got about a 16-foot suction height. So basically you've got sample coming up through the filter, in through this sample pump, and it comes in this small bracket right here, or this push to connect fitting, and it'll go through the pump and out of this push to connect fitting, which these fittings are really nice for commissioning because all you have to do is just push the tubing in and it holds it. It's got a nice secure fitting. And so this is what's actually bringing the sample in from the filter. And then it's going to push it to what we call an overflow vessel. And a lot of analyzers will actually have something similar to this. They might not call it an overflow vessel. We have on the 3017M, it's called the fill and spill. It's similar to the overflow vessel. But basically what this thing is it collects filtered sample and it just stores it here so that it can be ready for the next measurement. When the analyzer is ready to take that next measurement, it'll pull the sample from here. Now, this does have a drain. So the idea of the overflow vessel is it's constantly filling. This pump is running 24/7 and filling this up, and any excess is going to this clear drain tube down here. So you're always going to have a fresh sample to pull into the measuring unit when it's time to take the next measurement. So moving on, let's talk about the measuring unit itself. Now, a lot of people think that this is just styrofoam packaging. And in some cases, we've had people throw this cover away. And we've had people throw this cover away thinking it's just packaging, but it's a very important piece to this whole analyzer. What it does is it creates a controlled temperature environment inside of the measuring unit. That's where the reagents are going to be stored, the mixing chamber, and the actual measurement reaction is going to take place. So for accurate and reliable data, we really want to have a nice controlled environment. It's important. I mean, we're taking complex laboratory measurements, bringing them out into the field, and we're trying to mitigate as many variables as possible, whether that's through filtration of the sample that we were talking about, or controlling the actual reaction and the temperature and atmosphere around it. So if you notice here, we've got a blinking LED light, and this is going to be the key for this particular unit. It's going to let you know what state this measuring unit is in. So there's 4 different colors. There's a red, there's a green, there's a blue, and a white. And quickly going through that, the red means there's some sort of error going on and you need to stop and look at the logbook on the controller. A green light means it's either ready for operation, or it's ready, or it's measuring, cleaning, or calibrating. So it's running through its normal paces. A blue light means that the ELISA has been manually stopped, but this cover is not ready to be pulled off. And then the white LED that's flashing right now means that it's been manually stopped and it's ready to be pulled off. And the difference between the blue and the white light is basically, like I was saying, we want to keep this temperature very controlled. We keep it at 20 degrees Celsius, and that's to help optimize the reagent lifetime and the reaction. And if there's a vast difference in temperature on the outside air to that, we could cause rapid condensation to build up in the photometric unit over if you just pull this off without letting the temperatures come and level out. And what that will do is that will either wreck the photometric unit or it'll cause inaccuracies in the measurement. So we, just by running a simple command on the controller, it'll start to equalize the pressure and temperature between the outside air and inside this measuring unit, which we just did before. So we can go ahead and pull this off, and the air conditioning unit, you can hear it turned off because there's no need to run it while we're in here doing maintenance activities. So we were talking last about the overflow vessel. That is going to pull sample into what we call a mixing chamber. And the mixing chamber is basically where the reagents and the sample are going to meet. And for this particular unit, we use something called an MPV. It's called a multi-port mixing valve. And it uses microfluidic technology to ensure that there's only a small amount of sample and a small amount of reagents being used per measurement. So that is held in this MPV locking device. We'll get into this a little bit later when we get into the maintenance protocols. But every analyzer that's doing a colorimetric measurement or any sort of has reagents where the sample and the reagent need to mix is going to have some sort of mixing chamber. Next, we have the reagents here. Now, these reagents are a little different than what you might be used to. A lot of manufacturers, including ourselves and other analyzers, use bottles for their reagent storage. These are IV style bags that hang upside down on a guide rod back here. And we do this for a couple of reasons. One, they come pre-mixed and they have self-checking valves so that there's no risk of spilling these reagents. I can shake them around as long as the bag isn't punctured. You're not going to spill these reagents because of the check valve. And also it minimizes the space needed and it fits nicely and compactly in here. So, but yeah, you'll see these in bottle format. You might see bag formats, and there could be even other formats, but you have to have a place to store your reagents within an analyzer. Next, once the reagents have mixed with the sample, it's going to go to what's called the photometric unit, where the measurement's actually going to be taken. And for colorimetric analysis, very quickly, you're mixing a sample and a reagent, a color change is occurring, and then a photometer is going to measure that color change and then run some calculations and spit out a measurement on the controller. Now, as you can see, we have this one doubly insulated, and that is for two main reasons. One, so that we can be more accurate, and two, so that we can speed up the reaction time. If we keep this at a precise temperature inside this unit here, then we are able to get that accurate and reliable data. And then finally, we'll talk about the drain here. So the drain is where everything, whether it's coming from the overflow vessel, just the sample, or the chemical waste is going out of the analyzer. And what's nice about this particular unit is you can separate that overflow vessel, just the wastewater sample, and you can send that straight back into the process if you want. And then you can separate the chemical drain out to a different one. And that's really helpful if you get charged for chemical disposal. So you can separate that drain and you're only paying for the chemicals that are coming out, not all the excess coming from the overflow vessel. So that is a nice addition on this particular unit. All right, so now that we've covered the basics here, let me put this back on, and then we will go ahead and get into the main pain points, really. What are the main pain points of online wet chemistry analyzers? Well, there's three, really. One is the reagent consumption, which that is kind of taken care of with the MPV on this unit. We're only using 4 to 15 microliters per measurement, which is nice because reagents are costly and they're also costly to dispose of. Another thing is the reliability of the data is another pain point commonly known with wet chemistry analyzers. I mean, we're taking laboratory practices and putting them out on the basin. So being able to get accurate and reliable data is extremely important in analyzers. That's why this one is double insulated, and we've got a 0.45 micron filter, so we can mitigate all variables that come along with measuring in an online out on the basin kind of application. So, and then finally, it's the maintenance, right? These are not just probes you're going to drop in and that you pull for cleaning and changing consumables every once in a while. There's a lot going on here. And because of that, wet chemistry analyzers are notorious for having a lot of maintenance and a lot of touch points, basically. But with newer analyzers, maintenance is really simple. Manufacturers have really thought it out and tried to make analyzers as maintenance light as possible. So first, we're going to talk about probably your most common touch point is going to be this filter. Without cleaning the filter, you're going to have a lot of issues with particulate matter getting in there and ruining other parts of the instrument. And also just, yeah, that's basically what will happen if the filter is not cleaned. To clean this, it's really simple. You pull it. Well, first you stop the analyzer and then you stop the sample pump, which it's just a button right here to hit stop. Once that's completed, you can pull this up from out of the process, take it off of its mounting, and basically you take a tub like here. The camera probably can't see it, but you drop it in a tub of just regular water. Hose water is fine, or tap water, and kind of just rinse it off in the tub. And then the ELISA comes with a brush. It looks a lot like a paintbrush because it basically is. It's just a soft bristled brush. And what you do is you just wipe off the excess material, and you can, it's a very quick process. You do it on both sides. If you lose this brush, you can just go down to the hardware store and get a soft bristled brush. No need to buy really a replacement one from us. I mean, it's really just a simple brush. And as long as you're doing that on a regular basis, that's going to solve a lot of the problems that could occur with a wet chemistry analyzer. So one of the big, well, I should mention, this is a mechanical form of cleaning this. You can do a chemical cleaning, depending on how dirty this filter gets. Unfortunately, we don't have time to run through that process with you, but essentially it's just doing the mechanical cleaning process that I just went through, but adding a chemical bath. So you mix up a chemical solution, you drop this filter into a tub for 30 minutes, pull it back up, rinse it with low pressure water, and then wipe it off and drop it back in. That's pretty much the difference between a mechanical cleaning and a chemical cleaning. Now you may be asking, how often should I be doing this, right? It really depends, like I said at the beginning, where this is deployed. If it's closer to the influent, then it's definitely going to need to be pulled more often and cleaned. If it's closer to the effluent, maybe you can get away with longer periods of time. What we recommend is that once you start up a wet chemistry analyzer and you drop the filter in, check it daily to see how it's getting dirty. And for this unit in particular, aside from those visual checks, there is a pressure gauge on the filter. And so what we always tell people in the field is, when you drop it in, note the pressure that it's pulling at. So it could be negative 0.4, let's say negative 0.4 PSI. If that's what it's pulling at with a clean filter, once it goes 2 clicks farther, so that would be negative 0.6, that's a good indication that your filter is starting to get clogged and the sample in the pump is using more pressure to pull that sample through. So in conjunction with just visually checking and checking this pressure gauge, you're going to be able to develop a protocol, whether that's pulling it once a day or once a week or once a month. That'll all just be determined on where it is in your process and what's in your particular process. All right, so next we're going to go through changing consumables. That's probably the next most common touch point. And what I mean by consumables, every analyzer is going to be a little different, but it's mostly reagents and then some wear parts. For this one, it's that MPV valve we were talking about. So what you do here is we're going to do a lot of work on the controller here. So we're going to switch to the controller view right now, and I will walk you through the paces of how to change these things out. Shannon, do you mind switching that? Thank you. All right, so now that we've got a good view of our controller here, what we're going to do for this particular analyzer, it'll be a little different for every analyzer, just depending on the manufacturer, but we're going to go to our ELISA menu by hitting that C button on the 2023G. And then we're going to go first, I like to check and see the remaining tab. And this camera may filter a little bit. It's got an auto setting, so bear with us on that. But what I'm really looking at is this reagent diagnostic screen to see when my reagents need to be changed. That's one nice feature about the ELISA is it'll tell you exactly how many days of reagents you have left. For this unit, you can see reagent A, we're down to 3. It's flashing and blinking. We've got 3 days left before we run out completely. So knowing that, we're going to go ahead and move over to the maintenance tab, go down to the wizards, and then we are going to run a replace MPV/ChemBag wizard. And this will be run every time that you're changing reagents. It's going to walk you through step I need to change. And so I'm going to check off, we're going to do an MPV change and a reagent A change. Those are the only two things I want to change right now. My standard solutions and cleaning solutions, as we saw in that remaining tab, are good to go. And then next, it's going to say, all right, we're going to run all these automatic things. We are going to prepare the measuring unit to be opened. We're going to prepare the locking device of the MPV to be opened, and we're going to drain any solutions back into the reagent bags that are currently in the tubing. So we're going to hit continue. It's going to run that process. And now it is going to tell me to open the doors, which we already have open for this webinar, and open the front cover of the measuring unit. So we're going to do that and click continue. And then next, I'm going to show you how to actually physically change the MPV and the reagent. So we'll switch back to the wide view here. And there's two main things that we need when we're changing an MPV out. I like to always have a paper towel just to wipe off any excess reagent in case that happens. And then of course, the replacement MPV. So what we do is we pull this locking mechanism down. I usually quickly slide under a paper towel, hold down firmly between the MPV and the top of the locking device, and then just slide it out and check for any reagents. Usually, if you've got a good working MPV in there, there's not going to be any sort of spillage or leaking. And then it's really simple. All you do is you lift up on the top, pull the old one out, set the new one with the logo out, and put it right on the guide rods in here and drop it in and go ahead and lock that back up. Then we're going to run an initialization of the MPV. You might be able to hear that. And that, what an initialization of an MPV is it's just it's checking every single valve in that MPV port. So each one of these streams, these lines here, are different valves for cleaning solution, reagents, standard solutions to enter into the mixing chamber and measure, clean, or calibrate, basically. And there's a valve on the back here that gets turned, and it's just making sure that all those channels on that new MPV are ready to go for operation. So this will take a couple of minutes, and while we wait for it to initialize, let's go ahead and talk about how often we're going to be changing some of these consumables out. So I've got the MPV. We change it out around every 6 months. We regularly are seeing them last 8 to 12 months in the field, but we'd rather be proactive than reactive. We don't want to wait until an MPV fails to change it. So we're recommending that we change these out once every 6 months. Now for the reagents, if it's reagent A on, if it's any reagent on the NH4, the ammonium analyzer, on measuring range 1 at a 10-minute interval, you'll be changing that out every 3 months. And then for measuring range 2 at a 10-minute measurement interval, you'll be changing that out every 1.5 months. The PO4 analyzer, it doesn't matter what measuring range, 1 or 2, the reagents will last 6 months at a 10-minute measuring interval. Now, of course, the measuring interval is user selectable for this particular unit. So 10 minutes is the lowest, I believe, measuring interval that you can select, but you can do 15 minutes, 20 minutes, 30 minutes, an hour, once a day. And of course, if you're going to elongate that measurement interval, the reagent's lifetime is going to increase as well. Now, the only other two solutions that we're worried about changing out regularly are the cleaning and calibration solutions, and those at a once a day cleaning and once a day calibration will be changed out every 6 months. And it should be close to being done here. But while we wait, this is a good time to talk about the third the third piece of maintenance, which is just really a visual inspection. And I'll get into this a little bit later after we change the reagent bags out. But a basic visual inspection once a day or once a week can really keep you out of trouble as far as just solving problems before they occur, right? So if we're checking different parts of this analyzer, and I'll show some hot spots here, each day or at least once a week, we're gonna solve a lot of problems before they even occur, because there are going to be some indicators that that present themselves before we get into any real issues. All right, so it looks like it's done. So that was a little precursor to the next piece. But if we switch back to the controller view now, I'll show you how the reagent change works. And basically, for a reagent change, it's all you have to do is enter the expiration date, which is located on each reagent bag. So this one says it is May 15th of 2024 or 2025 is when this one expires. So we'll put that data in, and then it'll ask you the filling level. If it's a new reagent, it's going to be 100%. And then you'll click continue, and then it'll go ahead and tell you to change the actual reagents out. So switching back to our wide shot, I'll show you exactly how to change the reagents. You mind switching the camera, Shana? Alrighty, so we've got the reagent bag here. We're going to pull reagent A out. And what's nice is these are color coded with what's on the bag. So it's got an A bead and a green bead on the actual tubing, so you know what to connect where. And so we'll just take off the old one. That pressure valve will go ahead and inactivate, making it spill proof. And then we will go ahead and put on the new bag. And it's really just as simple as this. The only thing to note is you just want to make sure you don't cross thread this, and that you firmly tighten this all the way down so that we make sure we depress that check valve. We have had in the past where a quarter of a turn does not, it doesn't depress that check valve, and it'll cause some errors to be thrown on the controller. So once that's done, we can go ahead and put the measuring unit back on. We can click continue through the wizard, and it'll ask you if it wants to start up. And it'll go all through its startup process and its checks, and then it'll start measuring again. But for the purposes of this webinar, we are done there. So I'm just going to put it in maintenance mode and actually, I'm going to keep this open, and let's talk about the visual inspection very quickly. So there's a few things that you want to go ahead and take a look at on a daily or weekly basis. One being the filter, and we talked about the filter for cleaning purposes, but you also want to visually check it for any perforations, because that is how particulate matter gets into the analyzer, and that causes tons of problems, especially with the microfluidics getting into the MPV ports. The pressure gauge we mentioned, that is another thing that is a good indicator when the filter is starting to get dirty. And then the overflow vessel is something I always look at when I'm going out on site. Why? Because if there's anything other than clear liquid in this overflow vessel, that means you have either a torn filter or some sort of breakdown between the actual process water and the sample collection system. And so that's a great indication on whether or not you might need to replace a filter or you need to check your fittings. So this overflow vessel should be clean at all times. The other thing I like to check is the drain tubes, just to make sure they're not kinked up. If we don't have a free flowing drain or chemicals going to the drain, there is a small chance that there could be backflow up into the measuring unit, and these reagents are corrosive. That's why I've got PPE on today. And we do have a collection tray in the bottom, but that collection tray can only hold so much before it spills over. So just making sure you've got free flowing drain tubes out to whatever drain it's going to is important. And then finally, there are a couple of air filters on here, which help the analyzer come to and from temperature. And so there's one on the top. If you lift this hood up, there's a standard air filter. And then there's one under the bug screen at the bottom, another standard air filter. And to ensure that we're getting accurate and reliable data, we need to make sure that the temperature can be controlled. And just like anything else, like your car or your house, you have to check those air filters from time to time to make sure we're getting quality airflow throughout the system. And with that, that is basically it. So the three main things for analyzer maintenance is filter, filter, filter. You want to make sure that is clean and operating smoothly. You want to know how to change out the consumables, and then visual inspection is going to keep you from dealing with a lot of problems. If you're not doing a visual inspection, things will start to decay and occur. So with that being said, we are going to take a quick break to transition between my half and John's half. Now would be a great time to ask questions and type questions in the chat, because you will not be missing any of the content.
Thank you, Justin. While they're doing the transition here, like Justin said, this is a good time to enter any questions you have so far in the Q&A, and we'll try to get to those at the end. If we run out of time today, we'll definitely follow up on any questions you have. And give us just a couple minutes, or actually a minute here, while we transition over to John, and we'll be right back with more live demonstrations. And while we're waiting here, quickly, just wanted to talk about CEUs. This webinar today is eligible for CEU credit hours, and there will be more information about that in a post-webinar email. We're going to do a quick camera check here, and then John will get started. All right, we're ready to go. John, take it away.
Once again, thank you for attending our webinar. My name is John Welsh, Product Manager at YSI. And the focus of this portion of the webinar will be on one of the most primary and important aspects of maintenance on the Model 3017M, and that's cleaning of the flow cell. Other aspects of the operation, maintenance, and setup and commissioning of the Model 3017M have been covered in other webinars and videos, and those are available on the YSI website. However, before we get started with the actual cleaning process, let me first walk through the important features of the instrument and how it works and how those impact what we're going to be doing today. The Model 3017M behind me operates in the principle of continuous flow analysis. In that type of analysis, what we have is, as this pump is turning during the break, I started this into the rinse mode. We have a sample pump, which is drawing sample from this container below it. If this were actually online, we would have our sample inlet device connected here. So sample is always continuously flowing across here and through the flow cell. At a predetermined time set by the method on the instrument, the reagent pump here will come on and deliver reagent for approximately 13 seconds. The reagent, the indicator, and the buffer are located down in this compartment below. And the most important part of the instrument is the flow cell itself. And this is the portion of it that will, over time, become dirty and require cleaning. The way this flow cell works, there's, of course, inlets and outlets for the buffer and the indicator. Sample flows in from this direction. Behind here and included inside of it is what we refer to as a static mixer. When the reagents mix with a chlorinated sample, the reaction happens very quickly. That turns to a pink color and flows up through the top of it and then out the waistline. Are we good? Okay. All right. Behind the flow cell and included on the electronics behind it, there's the LED source. These two devices in the front are light guides, which are taking the light from the LED source first through a reference channel and through a sample channel. So as light is passing through the flow cell, as long as that flow cell is clean and in proper working order, that light will be detected by the photodiode on the electronics behind it. As the cell becomes dirty, then that amount of light is decreased. The way the instrument compensates for that is by what we call increasing the gain on the detector. So, and it's that aspect of it that we're going to look at very closely while I go through the cleaning procedure. So with that said, let's get started. A few things that you will need, I have here a couple of containers of DI water. One I'm going to use and install here just a second. The other one I'll use for a rinse. And all that's required to clean this flow cell is a 50-50 mixture of common household bleach. No harsh chemicals, no concentrated acids, nothing like that. So the first step, there is a quick disconnect here at the bottom of it. I can do this while the instrument is running, and it's handy to have a source of clean water. This is DI water. If you have DI, that would be great. If you have very clean distilled water, that will work as well. First, connect this. Now we have separated the analyzer from the sample, and we're drawing water here. We're going to use this to rinse this after the cleaning procedure. The next step, and I will just do this real quickly, is to put the instrument in shutdown. Shutdown does not turn it off. What it does, it prevents it from going through the analysis cycle. And then the next step, at the bottom of the flow cell, this plug is referred to as the cleaning port. Inside the startup kit for the 3017M, one device you have is the cleaning syringe. So after I remove the plug, these are 1/4-28 fittings. I secure this tightly, and I will take my syringe and draw up about 10 milliliters of my 50-50 mixture. So now, Shannon, if you will switch camera views. Okay, you should be seeing the screen. And the first thing I'm going to do is go to what's referred to, oh, sorry, I went past it. The status screen. On this screen, what we see is the condition, an indication of the condition of the flow cell. At the top, these are the voltages being generated by the photodiodes on the reference and sample channels. Below it, the first number, the reference, the next number after that, the 1, represents the gain. So the reference channel in this instrument has a gain of 1 and approximately 16,000 counts on the reference channel. The sample channel also has a gain of 1, but you'll see that's at 10,000 counts. The threshold for this instrument, for the instrument electronics and firmware, somewhere around 15,000 counts. So it's quite possible this instrument might be slightly dirty. So if it were extremely dirty, what you would have seen is that this gain value may be up as high as a value of 8. And once it reaches that, which is the maximum gain that the firmware allows, and if this signal continues to drop below the threshold value, then you're going to get an alarm at the top of this says auto gain error, which means the instrument can no longer compensate for the loss of light that may have occurred since the flow cell became dirty. In the primary applications for this, being the drinking water and the wastewater application, in drinking water, it's very possible that this instrument could go for a year, if not longer, without requiring any type of cleaning. In wastewater, that situation's a little bit different, since the 3 primary points that we monitor are the feed, and then we have the post-disinfection, where amount of that feed has been consumed by the wastewater, and then gives an indication of the amount of chlorine that will have to be dechlorinated before the final effluent, and then finally the final effluent. In drinking water, it's not so much of a problem. In wastewater, what tends to happen is that any types of screens, filters, anything else upstream of the instrument have lost sample flow. Then we do not have the cleaning action of the water that's continually flowing through the flow cell. In drinking water, if you think about it, we have a slightly chlorinated sample that's continually flowing through the sample cell, and thereby acts as a self-cleaning mechanism. So what I will do next is attach my syringe to this portion of the tube, and I'm going to slightly inject very slowly and I'm down to probably around somewhere between 6 or 7 milliliters of cleaning solution. And if you observe, you can see that the signal is slowly starting to come up. Had this instrument been extremely dirty, say we were around less than 2,000-3,000 counts, 1,000 counts, this would be a little bit more dramatic. And so as the cleaning solution is removing whatever type of contamination might be on that flow cell, you can see this start to come up slowly. Now, usually at this point, I advise customers or anybody else who's cleaning one of these, this is the good time where you allow this about 5 minutes to react and completely clean the flow cell. In the drinking water application, that's usually all it's going to take. It all just depends on how dirty this flow cell has gotten. So what I'm going to do is go ahead and push it in one more time. And the reason I have the DI water is that I want to rinse that flow cell of all that concentrated chlorine before I restart the instrument. You can see it respond because it responds to the changes in flow rate that are happening. Now, this particular instrument may not have been extremely dirty, but we now know it's probably very, very clean. So what you will want to do is do that at least 2 times. Okay. That should be enough for the initial rinse. I'll just set that down. The reason you see it going back down is I probably injected a little bit of air into that flow cell. Remove that portion of the cleaning syringe. Return your plug so we don't leak out when we start back up again. And then again, because I now have this clean water down at the bottom, what I will first go through is I come all the way back out again. And I will go through rinse. In the rinse command, what happens is that you hear the pump starting up. Just the sample pump turns, and it turns at a higher rate than it normally does when the instrument's running. And what it is doing, as the name implies, it's intended to rinse the flow cell of whatever might happen to be in there. So if we want to check our signal again, it's menu, status, and we aren't changing very much because this flow cell may have been fairly clean to start with. Prior to the video, I'd been running some tap water here at the factory, which had approximately per million in it. And if there had been anything there, then you probably would have seen it, probably would have cleaned it out. So we let it rinse for a little bit. And the next step that I typically do, because we've been using a concentrated solution of chlorine and we measure chlorine at very, very low levels. One way, and a good way to check to see if all of that chlorine has actually gotten out of the flow cell, is to put the instrument in prime. When I place it in prime, again, not only does the sample pump start, but the reagent pump starts as well. So now we're adding water and reagent to the flow cell. If there's any residual chlorine from the cleaning procedure, there'll be a slight pink coloration you'll see in the waistline. If I go back to my status screen, you'll notice that the signals drop now to approximately 7,600 counts, something like that. And that's because the reagents are mixing with the residual chlorine that was left from the cleaning procedure. And as that is swept fully out of the flow cell behind here, you'll see the signal start to come up. And what I would do in this instance is wait until that signal came back up to whatever that starting point was. In this case, it was around 10,000 counts. And that would be a good indication to me that I thoroughly swept out all of the residual chlorine cell. Again, and we'll just allow that to keep coming up, and I'll come back to the main screen. One thing I can touch on, if, for instance, this analyzer had been extremely dirty and we were up at a gain of, say, 6, 5, somewhere that high, or 8 possibly, what you would want to do is go into the setup. There's a command for A to D gain. Channel 1, which is the sample channel, and force this, manually force it to 1, because we want to try to start at the lowest gain setting possible. In this case, we didn't have to do that. That's only in the case where it's up very, very high. So I come back out again. Let's just take a look and see where we're at. I won't go through it completely. Now, we've rinsed for about a minute or so, and the signal's coming back up to where it started. So the process for cleaning this instrument is relatively straightforward. Again, all you need is a 50-50 mixture of bleach. As far as bleach goes, household bleach will work. One note about bleaches that are on the market, we like to use the liquid bleach. There are bleaches out there, the splashless variety, that have some type of coagulant in it. I would not recommend using that because I don't know what's in that stuff, and it's probably not great for cleaning an analyzer. So we just use the very liquid bleach. You'll need some clean water to rinse it. And I use these types of vessels when I'm doing this type of operation, because if you're running an analyzer that has a high chlorine content or sample with a high chlorine content, this is a very convenient way to just rinse the analyzer with clean water. And going back through the steps again, you would first stop the analyzer, then remove the plug, prepare your solutions, attach your syringe, and then inject it, wait, monitor the signal on the status screen. And when you've reached the maximum, the highest value you can possibly reach, wherever the instrument goes, because there's not any one set point that it's going to actually reach, but as high as it's going to go. And then once we are convinced that we've thoroughly cleaned this, the next step to put the instrument back into service is go to startup, and you can do this on the fly. Push the button. Now the instrument's going to go through its startup sequence, which is again going to do some of the things I just did manually. It's going to rinse it, prime it, set the gain on all the electronics, and while it's doing it, you can just simply take your sample line, push it back in the 1/8 inch quick connect at the bottom of the instrument. I am now connected here and drawing sample from this reservoir. That happened to be your sample. And with that, that covers everything that I wanted to cover today. If you have any questions, we'll be happy to entertain them. And hope you have great success with your 3017M in the field. Thank you very much.
Thank you, John. We do have a few questions that came in during the webinar. Let me just. Okay, so the first question is, can the ELISA reagent bags be refilled?
No. They are factory sealed, and if they need to be replaced, they have to be replaced in that bag.
Okay, we have another question here. In wastewater applications, can chlorination stage influent, effluent, and dechlorinated effluent all be measured with the same online instrument? And if so, what is the residual chlorine detection limit for the dechlorinated wastewater?
Okay, in the applications that we've done, we've actually deployed 3 instruments for each of those individual streams. Theoretically, you could probably do it with 1 instrument. However, there would have to be some kind of command and control process that advised the operator, the DCS, wherever the data is going, that you've actually switched streams, and we're now monitoring going from feed to dechlor to final effluent. I guess in theory it's possible. In practice, we haven't done it that way. We've just dedicated an analyzer to each of those streams. And what was the second part of that as far as?
If so, what is the residual chlorine detection limit for dechlorinated wastewater?
The instrument has a limit of detection of 30 parts per billion. We typically analyze, well below 50 parts per billion, which is a typical effluent stream.
Okay, thanks, John. What's the shelf life of the DPD reagent?
These reagents, once they're mixed, are going to last for 30 days if this instrument is running the normal cycle of 2.5 minutes. Our reagents will last at least 30 days. They will sometimes go longer than 40 days. But because we ship reagents dry, they are not mixed. The shelf life, if it's stored in a cool, dry place, is 5 years for all the powders. The DPD is typically 1.5 years. But once they're mixed, if the instrument is running 24/7 at a 2.5 minute cycle, you're going to consume them within 30 days.
Okay, thank you, John. We have time for one more question. Looks like Justin, can you take this one? The question is, how often to inspect the air filters on the top and the bottom of ELISA?
Yeah, so with the ELISA, it's just like the filter. So there's no real time that I can give you. It's just going to depend on the air quality in your area. If you're at a new construction site and there's a lot of dust flying around, then of course you're going to have to replace them sooner than if you're in maybe a place with better air quality. So just depending on where the ELISA is deployed, I would recommend, I know I recommended doing visual inspections once a day or once a week, but with the air filters, you can go a little bit longer, maybe once every couple of months. Just give them a quick visual inspection. Maybe it's when you change reagents, you add that into your protocol and actually just, change your reagents, change your MPV, and then also check the filters, make sure they're cleaned. And you don't have to replace them every time, kind of like with car filters or shop vac filters. You can clean them out and they can last a little bit longer, but eventually you will have to replace the filter mats, over years of service. But practically speaking, I don't think they've caused problems in the first couple of years of deployment. But we did notice at the year 3 mark, depending on the air quality around, we had some ELISAs with issues coming to temperature. So hopefully you can find an answer in all of that. And we just want to thank you for joining the webinar. I think we are getting close on time. So thanks for tuning in for the full hour. And we appreciate you taking time out of your busy schedules to listen in about analyzer maintenance.